to record to this computer. Okay. Cool. Okay. Yeah, thanks, Nick. Just in case you get kicked off or something. Yeah, we'll probably give it another minute or two. Let people come in.
You want to put up the welcome?
Ah, that's a good call.
Okay. You want to take it away, Andrew?
1 second, I've lost my mouse.
Oh, okay. Better go find it.
I actually have no idea where it is. Jonah, I've not used Keynote before. Does Keynote do this?
I know.
Oh,
I'm
oh
sorry.
no, it's okay. Okay, well,
I think you can use the arrows to right arrow to advance.
okay, let's just do that. All right.
Okay.
Great. Thanks everyone for coming. Today, so yeah, welcome to the 33rd ECS and Cloud Feedback Virtual Symposium. So we're on a, just to remind everyone, we're on a Tuesday today. Normally for the past few months, and in the future we'll be on a Monday, but today is a Tuesday. And yeah, we're really excited today to have a panel discussion on the topic of, are recent tropical SST trends forced or unforced? And it's I think we're really lucky to have two great speakers who are going to present different sides of this topic. So we have Peter Huybers, who's a professor of Earth and Planetary Science at Harvard University. So Peter got his PhD in 2004 from MIT. And since then, he's worked on a range of topics in climate science. And particularly exciting for us today is he's done lots of really kind of fundamental work on climate reconstructions using proxy data. And then in the other corner, we have Rob Wills, who is an assistant professor at ETH Zurich. So Rob got his PhD in 2016 from Caltech and has spent a lot of his career working on climate variability, using a range of different methods from theory, simulations, and data-driven techniques. And so, yeah, we're going to hear from them today. And just a few notes before we jump in. So the structure is going to be a little bit different today. We're going to have two 15-minute talks. I'm going to give a 2-minute warning. And then after the talks, or if people have questions purely of clarification, they can ask that. And then after both speakers have given their talk, they'll have an opportunity to briefly respond to one another. And then we'll hopefully have a lot of space in the second half of the hour for open discussion. So, think of your questions, think of broad questions that you might want to ask or discussion points you might want to bring up. This is a big question that encompasses large parts of the Earth system. So we think that there's a lot still for us to kind of converge on here. Yeah, and if you have questions and comments, you can type them into the chat and we'll come back to them later. If you prefer to ask questions, you can also raise your hand, we'll unmute you. And yeah, we have our executive committee. So Nick, Shia, me, Jonah, and Andy and Christy, who are emeritus members of the committee. It's a group effort. And we also have loads of a backlog of numerous talks, some of which are going to be are relevant to the topic we're thinking about today. So if you are here for the first time and you enjoy what you see, then go to this mailing list, go to this website, sign up for the mailing list, and have a look at some of the past talks as well. So with that, I'll stop sharing. And Rob, if you want to take it away.
Okay, is all looking okay on the screen sharing front?
That's good to me.
Yes.
Okay, thanks a lot to the organizers for organizing this very interesting discussion, and really looking forward to it. And so for those who are hoping for a very contentious debate, I think we're not quite going to provide that, but hopefully we're going to provide some interesting discussion with two slightly opposing viewpoints of what could be causing the recent SST pattern trends, focus primarily on the tropics and focus primarily in the past 40 years, which is approximately what I'm showing here in this figure. And I'll show more details about this soon. So I'm not necessarily going to say that all of this pattern is forced, but saying that part of it is, or at least we should be considering the case that part or maybe most of this is forced, and that it could be showing discrepancies in the forced response in our climate models that we need to understand. This is drawing from one of my own papers and one paper led by Maria Rugenstein, and that are primarily presenting the problem and showing this discrepancy, and then some more recent work by the ForceMIP project and also by a project led by Pedro Dinasio that are potentially providing some solutions to what is the force response in reality. So overall, I'm going to be focused on how can we say what is the force response from this recent SST patterns. First, just a little bit of context. I'm going to zoom in on what is the system we're talking about here today. We're primarily going to be talking about the tropical Pacific and the SST patterns, which are important because they're the mediator between what's going on in the atmosphere, things like the overturning circulation of the atmosphere, the Walker circulation, which also has important implications in forcing large-scale waves that influence other regions. And then beneath that, then the ocean subsurface, which is often forgot about in this problem. And I'm not going to be talking a huge amount today, but I just want us all to remember there's also important things going on in the subsurface, and that the reason for this cool East Pacific is from these upwelling waters in the East Pacific, and that we also should be digging into understanding what's going on in the subsurface in the context of these recent trends. So then, as we look into what happens in the future, there's some different mechanistic ideas for what should happen. The one on the left, which primarily comes from an atmospheric perspective, is that we should have more warming in the East Pacific and a slowdown of the Walker circulation, where this comes about because a warmer and moister atmosphere increases the energetic demands to sustain the same zonal evaporative contrast or the same convective overturning circulation. And this has been supported by general circulation models for multiple decades, always showing this robust response, at least in equilibrium. However, the observations have been showing something more like what's shown on the right, with a La Nina-like warming, meaning relatively less warming in the East Pacific or even cooling, and a strengthening of the Walker circulation. And this could come about because there's delayed warming of the upwelling subsurface water, the so-called ocean thermostat, that's primarily a transient mechanism, so that shouldn't persist to equilibrium, but could be very relevant for the coming decades. And you can also have a La Nina-like response due to shifts of the intertropical convergence zone due to, for example, aerosols or other non-greenhouse gas forcing that then preferentially show up in the East Pacific and can also influence these temperatures in the cold tone. And the reason we're talking about this in a climate sensitivity and cloud feedbacks symposium has big implications for clouds and climate sensitivity. So I just want to get everyone on the same page by talking about the mechanisms for why this is important for climate sensitivity. So then zooming in on what's going on in the atmosphere here, if we put some warming in the East Pacific, this remains trapped near the surface because there's inversion in East Pacific. And basically what this SST warming does, if I switch back and forth between these two slides, is it's eroding this inversion in the East Pacific and reducing the low cloud cover. Because of this reduction in cloud cover, it then is associated with positive feedbacks that then can increase climate sensitivity if you have more warming in the East Pacific. On the other hand, if you warm in the West Pacific, this is a deep convecting region, and this temperature anomaly can be communicated aloft along the moist adiabat, where then gravity waves help to communicate this horizontally, maintaining a weak temperature gradient. So then this warming in the West Pacific influences the whole tropical upper troposphere. And this, in addition to influencing things like the lapse rate, will increase the estimated inversion strength in the East Pacific and increase the low cloud cover there. And therefore, having a lot of radiation go out to space due to the reflection from these low clouds and lower climate sensitivity. So these mechanisms have been explored, for example, in modeling work by Yue Dong in 2019. And this has been thought about a lot in the pattern effect community. And for example, this recent paper that I'm referencing by Kyle Armour and Christy Porcesescu explores the implications this has for these recent SST trends have for climate sensitivity, saying that because of this uncertainty about whether the SST pattern trend is forced or unforced, we have less certainty about what the climate sensitivity is from the observational record. So now, looking at these trends, this is showing then the comparison between observations on top and the multi-model ensemble mean on the bottom. And so here you can see that the observations have been warming, with more warming in the West Pacific and even some cooling in the East Pacific, whereas the models show more uniform warming with slightly more warming in the Eastern Equatorial Pacific. So this El Nino-like response showing up here that then shows up more further into the future. But this is not a like with like comparison. In the models, we're averaging over many ensemble members from many different models. So this is only showing the model representation of the forced response. On the other hand, in observations, this is just a single realization of the forced response and internal variability. So it also has a contribution of internal variability to this trend pattern, as well as observational uncertainty. And I'm going to leave observational uncertainty aside for now. Peter will talk about that more in his talk. But I'm going to talk about how much of this discrepancy between the SST patterns that we see on the top and on the bottom can be explained by internal variability. So what we can do is just look at how the difference in trends between top and bottom compares the spread of trends across the model ensemble. So how much of this trend discrepancy can be explained by internal variability? Showing that in terms of this metric phi, which is basically a z-score, or the trend difference in units of ensemble standard deviations. So the way you think about this is if you have a region that has greater than a plus or minus 2 anomaly, this means it has a less than 5% chance that this discrepancy occurs within the models. So these are regions where the difference between the observed trends and the model trends are not well explained by the model ensemble in terms of their combined forced response and internal variability. And so this shows discrepancies in particular in the tropical Pacific and then also the South Pacific and Southern Ocean. And if that metric's a little bit abstract for you, I'm showing this a little bit different way here, zooming in now on just the tropics and showing two different metrics of tropical SST pattern changes. On top, I'm showing the difference in SST trend, still all 1979 to 2020, as I've been showing earlier, between the West Pacific and the East Pacific. So with the boxes shown here. So showing this strengthening of the SST gradient in observations compared to the weakening in almost all models. And then in the violins, all these different dots show what the individual ensemble members can show within the models due to internal variability on top of their forced response. And then on the bottom, I'm showing another metric that's a little bit larger scale, which is the relative warming of the warm pool, shown as this big purple box, relative to the rest of the tropics. And so there's a few ensemble members that can get this in some models, but there's a clear discrepancy in some models where there's a lot of models that really aren't getting this relative warming rate of the warm pool, for example. And so the question arises still, is this discrepancy due to a problem in the modeled forced response or the modeled internal variability? We can see here that there is a discrepancy, at least in most of these models. And if you look across a few other metrics, you can see that no model gets everything quite right. But if we just focus on these metrics, some models clearly have a discrepancy. So what's causing this? Is this a problem with their force response or their internal variability? And the claim I want to make is that it must be both. We know that no model is exactly perfect, and we don't expect it to have the true force response. And so really what we're wanting to know is what fraction of this is force and what fraction of this discrepancy is internal variability. And so it's useful to take the example of CSM2, which is model E in what, as a kid, I would have called dinosaur green. And it's the model that can most consistently simulate the trends in these two tropical indices, in particular, this relative warm pool warming rate. It has a bunch of models, a bunch of ensemble members from its 100-member ensemble that can get the observed trends. But if you look at its force response, it's higher than all of the other models. So this suggests that if CSM2 is a perfect model for tropical SST changes, this still means every other model is biased. And so kind of going through different scenarios like this, you always come to the conclusion that there must be some force response bias in models. And maybe CSM2 is getting close to the right answer for this warm pool warming rate, but there's still some model bias in some combination of these different metrics that we want to uncover. So then take, for example, one other model, which is MPI ESM, shown in pink, and it's the model that is second closest to representing the trends in these tropical indices. And while it also has more relative warming of this warm pool region than any other model besides CSM2, on the other hand, if you look at the top plot and this SST gradient change, these are the two extreme end members of what the model ensemble shows, with the MPI showing the most La Nina-like force response and CSM2 showing the most El Nino-like response in this narrow equatorial band. So I would argue based on this that it's very likely that the models on average are underestimating this relative warming of the warm pool relative to the rest of the tropics, but they're potentially closer to explaining the spanning the range of force responses that could be the true force response for this equatorial Pacific SST gradient. And just in case you think this is kind of cherry picking of some recent period that has this large discrepancy, I'm showing here how the discrepancies actually get larger for longer trends. I think this is also a good indication that the problem is in a big part forced, because the force response will have a larger signal to noise ratio relative to internal variability as you go to longer timescales. And so this is showing the multi-model mean of this phi metric that I showed a few slides ago, just for the west minus east SST gradient, and showing how it's sensitive to start year of the trend and end year of the trend, with the longest trends in the bottom left and the shortest trends on the along the diagonal. So while there's variability in both directions in this SST gradient, as you look along the diagonal in these decadal timescales, as you go to the longest term trends, you get this consistent discrepancy where models are not warming in as La Nina-like a fashion as the observations. And I'll note, because it's interesting to this community also, that this paper also shows that there's a relationship between how well models can get this decadal variability and on the how well they can span this range of decadal variability along the diagonal here, and what their ECS is, with the high ECS models, except for CSM2, less able to reproduce the decadal swings in the SST gradient. But then I'm thinking that as we focus more on the longer time scales, this is more the force response pattern that we really want to understand why this discrepancy is occurring. So I'm not saying exactly then what fraction of this is forced and unforced, but I think we can try to go in this direction. And so basically, rather than testing whether it's possible that the observed trends can be explained by models, I think we should be trying to figure out what the true force response is. I'm going to show two ways we can go about doing this, one based on statistical analysis and one based on models. So first, I wanted to present this force component statistical method intercomparison project, or ForceMIP, which is basically aimed at exactly this question of what is the force response in observations. And then once you know that, you can say what is the discrepancy from the models, and use this as a way to evaluate the models. So how ForceMIP works is participants, and I'll list all the contributors that have contributed this on the next slide, develop statistical or machine learning methods that can take a single realization of the climate system with all of its internal variability on top of the force response, as well as some training data based on climate models, and estimate what is the spatio-temporally evolving force response in this single realization. Then the idea is to test how well these methods work within some subset of large ensembles, including some that are not seen within the training data, see which methods work best, and then apply the best methods to observations. So this project has gotten a lot of interest from different groups submitting many different methods, different ways you can do this, including complicated methods using neural networks or other machine learning methods, or simpler methods involving timescale separation that basically says the force response is what's happening on the spatial pattern evolving in the longest timescale, for example. You can also use some kind of fingerprinting approaches that say that the force response should look like what it looks like in models, and then looks for how it evolves in observations. Or you can use some regression on some global mean surface temperature or forcing time series that you think encapsulate the force response. So there's 27 methods so far total, and I've done some preliminary analysis of which methods work best. Can't get into all the details of that now. I just want to show a result targeted on this these trends over this 1979 to present time period, where I've shown again for this extension to 2022 the observed trend and the multi-model ensemble mean trend. And now I've just slightly cherry-picked the two most skillful methods for this evaluation target of the pattern correlation of 1979 to 2022 SST trends. So basically picking the methods that are most skillful for exactly the question that we're interested in here today, and showing what they say is the forced response in observations. And in both cases, they show relatively less warming of the East Pacific compared to the West Pacific. So suggesting that part of this discrepancy, this La Nina-like warming is indeed forced, although they both do attribute then another sizable portion of this to internal variability. And it's interesting that there's actually some good agreement between these two methods, because I'll note they're very different in their approach and their complexity. The top approach is using some relationship of EOFs with the forcing time series, and it only has 15 tunable parameters. So it's really constrained to the observations. It can't use a lot of information from the training models. On the other hand, this second method is an internal variability filter based on a UNet, which is a convolutional neural network approach. And it has over 2 million tunable parameters. So it can really use a lot of information from the training models, which has some potential for overfitting. But that these two very different methods with very different complexities get similar answers in terms of what is the force response and what is internal variability is lending some confidence to this approach. I will say the caveat, though, that there are some methods that estimate that the observed force response should basically look like what it looks like in the multi-model ensemble mean, and those still have some skill. A little bit less skilled than these two methods, but then it means we can't quite know what the answer is entirely from these statistical methods. We do need to also improve our models so that we can maybe get so that they're not discrepant with the observations, and then can say what the force response is in this modeling framework where we can run multiple ensemble members.
2 minutes.
So that's what I'm showing in this last section of my talk, that shows that if you look at the force response in a high resolution model with a reduced double ITZZ bias, it actually has a forced response that does look a lot more like observations. So this is a high resolution version of CSM1 with a 1/4 degree atmosphere and a 1/10 of degree ocean, where they've run 4 ensemble members. So you can start to get at what is the forced response by averaging over this ensemble. And while this is a small ensemble, the circles, the open circles that are shown in the right plot, show where the trends in this high resolution model are outside the distribution of any possible 4-member subensemble from the CSM1 low resolution large ensemble, which is an otherwise equivalent model other than the resolution. So in all these cases, this high resolution model is bringing things closer to the observed trends in a very convincing way that's outside the distribution of the low resolution ensemble. So what can we learn about why this is happening in this model and not in other models? And so this is work that's in prep by Pedro Dinasio, led by Pedro Dinasio. And basically, what we think is going on is that it's related to the climatological bias in the ITZZ. And so this is showing now the trends focused on half of the year, December through May, in the low resolution large ensemble, this high resolution ensemble, and in observations. And so that's the SST trends, and then superimposed on that, you see these contours of precipitation. And unlike in the high resolution model and observations, you see this really pronounced double ITZZ in the Southeast Pacific in this season. And the mechanistic argument is that the relative cooling that can arise here in response to a lot of different kinds of forcing will then propagate into through the wind evaporative SST feedback into the equatorial Pacific, except that when there's this double ITZ in the lower resolution models, it gets blocked by this, and the anomalies are communicated aloft. It then can't penetrate all the way into the tropical Pacific. And that if you get rid of this double ITZ bias, these patterned anomalies, this relative warming or even cooling of this region, can then influence East Pacific, where it engages the Bjerknes feedback and can cause a Walker circulation response, which also has teleconnections into the Southern Ocean, which can help to reinforce this initial pattern. And this two-way teleconnection, which has been discussed nicely in a paper by Yue Dong, is basically amplified in this higher resolution model. And this is all thinking about the historical trends up to present, but one question you might be wondering is what happens next? That's a big topic, why we care about why there's discrepancy in this historical, is we want to know what's going to happen into the future. So what I'm showing on this final slide of results is then a comparison between what the forced response as represented by this 4-member ensemble average in this high resolution ensemble looks like for this comparison of 1980 to 2022, which is what I showed on the last 2 slides, to then going forward, 2023 to 2050. And what I think is really fascinating here is that the trend going into the future is dramatically reversing. It's no longer looking La Nina like it's very actually going quite strongly back the other direction and warming in regions with strong positive radiative feedbacks, which would just be associated with increase in the climate sensitivity over this future period. So if this model is indeed getting the forced response right for this historical, or is getting this SST pattern right as a forced response for the historical period, then this is troubling in suggesting that even if it's forced, it could revert back towards more El Nino-like warming in the near future, projecting onto more positive feedbacks and a larger warming rate and transient climate sensitivity. So with that, I'd like to wrap up, and just in response to the overall question of, is this recent tropical SST trend pattern forced or enforced? So this recent trend pattern shown again on the top left here, I would argue that it has to be both. Some of this pattern is certainly internal variability. We know internal variability influences trends on these timescales, but I think there's good cases that we should expect that there are some systematic climatological systematic trend biases related, for example, to systematic climatological biases like the double ITZZ bias. We know there's biases in the climatology, so we should expect that they're influencing also the response to climate change. And I've shown that you can statistically estimate what the forced response is from observations. This is preliminary results from the ForceMIP project that I'm showing one snapshot of above. But there's large uncertainty still in estimating what the forced response is from a single realization. This isn't going to get all of the answer on its own, but it gives a good starting point to at least have something more like to compare ensembles, model ensembles forced responses to. But I think ultimately we need to find what's going wrong in our models and fix these problems. And so, for example, if it's related to the double ITZ bias, which I think there's this recent work is making a convincing case that it is, then figuring out how to fix the double ITZ bias, which has of course been a topic for a long time in the climate modeling community, will then also have positive effects on fixing the SST trend pattern biases that I've been focusing on here today. So with that, I'll end, and looking forward to Peter's talk and the discussion afterwards.
Thank you so much, Rob. That's really wonderful, very informative. Let's just say if there are any sort of just narrow questions about clarification, Rob's talk that anyone has, maybe put them in the chat or raise your hand, but if not, I don't see anything. So, okay, we have one question from Gavin here. If the mechanism proposed is correct due to the ITCZ, one would predict that the models with better or worse ITCZ will have predictable rates of Eastern Pacific warming and cooling. Is that something that you've seen or have a comment on?
Yeah, so I think that's a good thing to look into. The problem is that the low resolution models all have such a strong double ITZ bias, especially in this half-year season that I was highlighting, that it's quite hard to find a model that's eliminating this to the extent that you can have this mechanism where these anomalies propagate into the tropics. But I would expect that if you do find such a model, that it would potentially show this response.
Okay. We're getting some more questions, but I think in the interest of time, we're going to move on. So thank you so much, Rob, and Peter, maybe start to put up your slides and take it away.
Okay, will do. Thanks for setting the stage there, Rob, and I agree. We are going to end up agreeing on a lot of things. But I'll try to provide a little bit of counterpoint in so much as I can. So there's really just three things I want to share. I want to talk a little bit about recent trends. I want to talk about the hiatus as a bit of a cautionary tale, and then dwell a little bit on what the magnitude of multi-decadal internal variability might be. So, broad picture that there is consistency when we think about the full uncertainty of simulations, and this is just one way of getting at some of the uncertainties. But, as Rob pointed out, when we look specifically at the mismatches that are occurring, this kind of evocative pattern emerges. I kind of thought, hey, it's an El Nino year. If I just update this, it'll go away and we can all be done with this. It turns out that that's not the case. It is warmer. If you download the HAD ISST data, that comes up to last month. We can see the El Nino playing out in global temperatures. You can see that if you fit a trend, again, starting in 1979, but going all the way to the most recent months, then of course it's going to be a little bit of a steeper trend because we've had this excessive warmth. I had expected that you'll see a strong El Nino pattern at the end, and that this would some way mitigate the pattern that had been previously found. But in fact, what you find is that the more recent trends actually show that pattern even more strongly than the trends that you compute from 1979 to 2020. There is additional warming, but it's the strong La Ninas that preceded in the Eastern Equatorial Pacific actually means that the pattern effect is more enhanced as we come forward in time. I take that as in some ways that's a prediction that turned out to be true. And so I find that to be more convincing than being able to find something that's identifiable when we're just kind of hashing through the data. This was predefined and still found. So that some ways argues against the side I was supposed to be taking, but I thought I should probably bring it up anyway. Next, the hiatus as a cautionary tale. So I thought, here's one way of looking at this, right? So Fife et al. Did a fine analysis in 2013. This was featured in the IPCC assessments. And, if you take the trend from different model simulations as a distribution of that there's each are equally likely, you can form a probability density estimate from that, and then you can look at the observations and you can do a model data comparison. It's a little bit like what we're trying to do here, right? How likely are the observed trends relative to the simulations? And you come up in the hiatus at the time, it looked like there was a substantial discrepancy. Okay, and so what did we do? Well, we try to explain it. And this, I should point out, this is an opportunity. It's very much what we should be trying to do. But, how we ultimately attribute a change to a particular set of mechanisms or particular forcing is a difficult business, and this highlights that, right? So one well-known explanation, which also deals with the tropical Pacific, eastern equatorial Pacific temperatures, Kosak and Shea showed, if you specify eastern equatorial Pacific SSTs, and everything else follows suit. And so that in some ways points to the importance of the tropical Pacific, and it's one, I think, still viable explanation for why we did see the hiatus when we did. The other thing that I found kind of surprising was that Tom Carl published this paper in Science and was like, oh, actually, we got the SST records wrong. We hadn't done the intercalibration between satellites and instruments correct. And the estimated warming is actually 0.086 degrees Celsius per decade, higher than what we had previously estimated, sorry, 0.05 higher, such that it's closer to 0.1 degrees Celsius, and then that really changes things. And so this is a reminder that even in the modern time period, we can still have instrumental SST biases that are non-negligible. We found it for the hiatus. It wouldn't surprise me in a much more data-sparse region like the tropical Pacific that there are kind of lurking systematic errors that are still present. So if you take the estimates as updated by Tom Carl for what the warming was during the hiatus, you get something closer to this 0.08 degrees Celsius per decade, and that puts us at the blue mark there, which is not really anything to write home about. That's on the low end, but it's not significantly discrepant relative to the simulations. And so we have a multitude of explanations, right? Our data can be updated or is uncertain in certain ways, and then of course our simulations are potentially biased. And if we came forward in time, then of course the hiatus goes away. And so we should just be careful when we note that there are model data distinctions, whether exactly where those arise from, have a multitude of potential sources. The last source that I really want to dwell on here is, well, what is the width of this distribution? And what should it be in terms of the universe of all possible SST realizations? The simulations obviously are just one way of getting at those, but those could be systematically biased in a whole variety of respects. For our present purposes, the variance of the estimate might be low, just based on simulations not producing sufficient internal variability, for example. So let me get to this question then. What is the magnitude of multi-decadal internal variability? It's a recent paper by Heat and Fedorov, and they point out that if you look over the satellite era at a number of kind of important indicators of what's happening in the Pacific, SST gradients, sea level pressure gradients, and surface wind anomalies, the reanalyses tend to show larger excursions than what the CMIP6 ensemble is showing. And so this is one indication that perhaps the intrinsic variability is larger than what might be being simulated presently. Okay. There's a number of other ways of looking at, well, what is the internal variability associated with the system? Here's a set of studies I did with Thomas Loppel some time ago now, but I think that they're still relevant. They haven't been shown to be wrong as far as I'm aware. So this is now relative to the CMIP5 ensemble, detrending SSTs, looking at the multi-decadal variability, in particular, filtering out everything that is higher frequency than 1/20 years. And what we're then doing is looking at the variance ratio. The observed observational variance relative to the model variance at places where we can go back for 100 years with SSTs as reported in the HAT-CRU ensemble is what's shown here. And the particular pattern that emerges is in the tropics. What we see is that the observations have around twice as much variance as the simulations. And so this isn't trends, but rather this is showing the other variability. But if the other variability in the observations is systematically larger, you might imagine that those would give rise to the potential for larger internal variations as well. Okay. I'll come back to an interpretation here. So one interpretation is that the observations show more actual internal climate variability. Another interpretation is that the observations contain low frequency noise that can kind of suggest greater variability, but is not in fact indicative of what the simulation should be reproducing. Okay. A larger issue in some ways is if we keep going out to lower frequencies, the discrepancy just gets bigger and bigger. So virtually all climate models, if you run them out for centuries, they basically go white in terms of their spectral representation. So here we're looking at frequency now in once per 1,000 years. So at the right-hand side, we have 1/500 years, and 1/500 kiloyears, or once per 2 years. And so we're going out from the 2-year time scale all the way out to the 500-year, out to the 5,000-year time scale at the very left. This is a logarithmic in the y-axis as well. So we're looking at spectral power density on a logarithmic axis. And in all the observations that we look at from paleoclimatology, what we see is a red spectrum. It continues to become increasingly variable. And so there's this kind of built-in discrepancy. The lower the frequency, the larger the discrepancy. It really becomes monumental as you get out to timescales associated with going over a lot of the Holocene. Right, we're looking at a factor of 100 difference in the variance once you get out to millennial timescales. Okay, and so we can kind of show this in a little bit like kind of a visual way. So if we look at interannual variability, as produced by simulations and then proxies at the location where we can compare them, and also subsampling for the appropriate seasons, you can see interannually they look more or less the same. A representative simulation in blue and available proxy records in black. Okay. If, however, we go to things that actually now record centennial sorts of variability, and so this is coming from magnesium-calcium ratios, you see this massive discrepancy. Okay, and so here you see this factor of 10, factor of 50 greater variance in the observations. For UK 37 alkanones, it's the same thing. Every paleoclimate record that we sample compared to simulations over these long time scales, when you're at an individual point, shows this massive discrepancy. I should say if you do global averages, you can get consistency. And so this is really talking about the redistribution of heat or local observational error that's giving rise to these issues. So let me just make a point about this this last issue. Some of the work that I got to do with Duo Chan, where we delved into systematic sea surface temperature errors associated with instrumental observations. The nature of the observational error here is interesting. Typically what it is you have one group of observers that is present in the oceans at a particular time, and then those are replaced by another group who make measurements in a different way. Maybe they use a different bucket, maybe they have different protocols for how they put the thermometer in the bucket and how long they wait on deck. And this leads to systematic offsets between the two. When you have a time series with a signal with noise that has this kind of step function behavior to it, but the step functions are randomly distributed in time, you get a covariance pattern that is shown in the equation here, and then you can take the Fourier transform and get a spectral representation. And the point here is that as you go to lower frequencies, you get increasingly much energy. And so this indication of greater and greater variability as you go to lower and lower frequencies could be representative of how the climate system works, or it could be representative that you get offsets that occur either in our instrumental records or perhaps with proxy records, that there's some sort of change in how species assemblages work or other factors. If you then look at the average across simulations across this is CMIP5 in the tropics, we look at the power spectral density in black. We have the HAD SST observations in red, and here I'm going out for a century, 2 different power spectral density estimates. You see this kind of gap opening up at decadal timescales, which is really the critical question. Is this gap true, or is it a representation of increasing kind of shot noise or error that's present in the records? If I do a estimate here where I've made a fit for what the shot noise characteristics are, the covariance I'm taking from the actual uncertainty estimates, and then I'm doing a fit, which is totally plausible for the amount of uncertainty that we've estimated for instrumental records, I can actually get a really nice fit between had SST plus noise relative to, CMIP5, and my observations are consistent when I take into account the fact that there might be noise present. Okay. The thing that one would want to do, of course, is subtract the noise power spectral density estimate from the observational power spectral density estimate, and then you would get the two lying on top of each other. Okay.
2 minutes. Oh, cool.
Perfect. Okay, so let me just recap. Recent trends have enhanced the pattern effect. Model data comparison in the context of the hiatus offers a cautionary example. Observations indicate greater variability in the simulations at multi-decadal longer timescales, but whether this discrepancy reflects greater internal climate variability or low-frequency observational noise is unclear. And then I just like to make the point that, what we're really talking about is attribution of recent SST trends, and attribution is difficult in this context. The magnitude of internal variability is poorly constrained. The simulated responses might be biased, and really the number of degrees of freedom that we have to work with here, I think, is somewhat debatable. There's a strongly covariant pattern. We're looking at multi-decadal trends. Maybe we really just have just a few degrees of freedom, which then makes a kind of statistical inference rather difficult. And so from the perspective of attribution, where we would want to reject a null hypothesis that everything is associated with internal variability, I'd submit that we're not at that stage yet. We can't reject the null of internal variability and thereby accept the forced response as the alternative.
Okay, thank you so much, Peter. That was a great talk. Maybe before we proceed to general questions, we just wanted to give you and Rob a chance to address each other. If there are questions that came up from each other's talks that you would like to ask, this would be a time to do it, and then maybe we'll open up to the floor.
I have one question about force MIP, which I think is a great idea. Let's try to figure out, how we can explain what's happening. But from this perspective of attribution, where we'd want to reject a notion of internal variability, do you see a route in that framework to be able to say with some high statistical significance that this is a forced response potentially?
Yeah, so I think it's challenging to formulate the correct null hypothesis, and this is actually getting into the question I was going to ask you, just related to your conclusions slide there, but I'll try to give an answer too. Which is this the right null hypothesis, that the null hypothesis is everything is internal variability? I think that is one question that we should ask, and then the answer, we probably can't reject that null hypothesis, but then I wonder if this is necessarily the right question to be asking, and we should, I think maybe more what I'm going towards is a bit more of a, we should be considering, it's not as rigorously statistical of a thing to say, but I think I'm more suggesting that we should be considering that the different possibilities that it's mostly forced or mostly internal, and that maybe can't be formulated in as precise of a statistical sense, but then I think force MIP helps to say, well, for example, the different estimates will give you different possibilities for how much is forced and how much is internal, and helps you explore that uncertainty about this question. But I don't think it will necessarily help you rule out the null hypothesis that everything's internal variability. I'm just not sure that's the right question to be asking all the time. It's definitely a question we should answer, but not the only one.
Yeah, that makes a lot of sense.
I guess then one thing I wanted to just ask what you think of. I think you probably agree with this, so it's maybe more of a comment. But couldn't some of this doesn't some of this low frequency paleoclimate variability on longer than decadal, especially as you get out to centennial or even longer time scales, doesn't this kind of go beyond what we're really representing in a pre-industrial control simulation? So including things that we might consider natural forcing, like volcanoes, which might be missing from these simulations, or also just Earth system feedbacks, which are kind of a blurry line between forced and internal in terms of things like how drought may trigger dust fluxes that then change radiative imbalances, or changes in the distribution of tree cover that then change surface fluxes, for example. Ice sheets, another good example.
Yeah, everything could matter. The volcanoes don't really help at beyond multi-decadal in general, at least for the power spectral density estimates. For individual time periods, if you had clustered or large volcanoes, they might. For the vast majority of the variance in these records, though, is local, right? It's not at these global scales. So when you start to average over an entire globe, what you might expect for some of the larger Earth changes or coherent forcing from volcanoes or solar variability, you'd expect to see that everywhere. It's really this regional internal variation that we both get a hint at from the SST instrumental records and from the paleoclimate records that is much larger than what we're seeing when we look in the simulations. If that is noise, it's sources of noise way beyond anything that we've quantified so far, and so we'd have something really important to learn there with uncertainty quantification. But if it's not noise, then of course that would also be very important to think about just what regional variability can look like beyond the kind of global averages.
Thanks. That's a really interesting point about the spatial scale of the discrepancy. To me, I think that suggests if it's really small scale that the variance is discrepant, that could potentially, this noise problem that you highlighted could be the answer there.
Yeah, that would be the simplest explanation from the kind of physical dynamic point of view, for sure. Yeah. But there's also, we know there's a lot of small scale processes that are missing from the simulations that are potentially important as well. So.
Well, great. Maybe let's start with Amy. Do you want to unmute yourself and ask your question if you can unmute yourself?
Can.
Okay.
Hi, thanks so much. What a great turnout. So also thanks to the organizers. Nice provocative titles, and we all show up. And an important problem. I really enjoyed the discussion back and forth. And Rob, I love, your point about the what is the right null hypothesis. That was what I wanted to ask Peter is, the disagreement whether instrumental record or long time scale can be between models and observations might be due to a third possibility, which is that models are underestimating forced response. And I think that's something we have to contend with. Cheng-Fei He, who's on paper here, has a paper looking at Atlantic climate variability on multi-decadal timescales and making that argument. And one other comment, is we're focusing on the SST records, but the instrumental record is richer than that. And I think we can, throw in some of our physical insights about how SSTs connect to other parts of the climate system, rainfall, circulation, sea level pressure. And we could probably be increasing our degrees of freedom that way. So just wanted to hear what you thought about the third possibility that there might be.
Yeah, thanks for bringing that up. I mean, if we look at let's say ITCZ excursions over the Atlantic and over sub-Saharan Africa, I think it's in response to aerosol forcing to some extent, maybe changes, differences in hemispheric heating. But the observed shift is larger than what the simulations tend to produce. And so here, we do see that coherent changes in response to forcing that are potentially large, potentially there's higher sensitivity there. And I think it's a good point and also worth looking at in more detail. Okay.
Okay, well, thanks for that question. I don't know if yeah. Okay, so we have a couple more questions in here in the chat. I'm going to go back to the beginning. So we had a question I think it's an anonymous question, just says from iPhone. I guess this is for Rob from your talk. How well does the LFCA method compare to the two that you showed in your talk?
Okay, that's getting kind of into the technical details, but so the LFCA is low frequency component analysis, and is a method that I've been working with for this problem for a bit longer than this ForceMIP project has been around, and have argued to be useful for this, and is in some sense inspiring ForceMIP. It's up there near the top of the pack, but these newer methods are doing better. I guess I would say that low frequency component analysis is the most consistent. It always gets a somewhat reasonable answer. These other methods do better for some metrics and then fail for others. So depends where your priorities lie.
Excellent. We have some hands up. Let's see, Andreas, I saw your hand go up first. Do you want to unmute and ask your question?
Yes, can you hear me?
Yep.
Yes.
Well, I was a little bit surprised by this high resolution CSM model simulation, that the forced response is so much different for shorter timescales than for longer timescales. For short, it looks like more like La Nina, and long, it looks more like El Nino. So why do you have any more insights, or why that happens, why the force response is so time dependent, and could it change then if you go even to longer time scales?
So this is something we're still looking into. I've looked at what's called a signal to noise maximizing pattern analysis to kind of tease apart the different patterns that are contributing to the forced response, and that hints that the pattern that's most relevant is evolving on a different, in a way you wouldn't expect it to in response to greenhouse gas forcing. I thought maybe reminiscent of the time series of response to aerosol forcing. So I think aerosol forcing could be really important in this model, but we don't have single forcing on simulations yet to test this. And there are other ideas about, for example, the ocean thermostat being too weak in low resolution models. And so I think there's different hypotheses that could explain this related to ocean thermostat in response to the greenhouse gas forcing, or the non-greenhouse gas forcing like aerosols.
Thank you.
Okay, we have another raised hand from Ori Adam. Do you want to unmute yourself and ask your question?
Yeah, hi. This is a question for Rob. I guess continuing what Gavin Schmidt said, given the pervasiveness of systematic biases, precipitation, cold tongue bias, thermocline bias, subtropical cell bias, can we really use statistical approaches in climate models to constrain the force response? I mean, regardless of sort of the null hypothesis of comparing, natural variability versus force, can we actually use these models? Can we trust them? So, I mean, are they inherently biased, so biased that we can actually use them?
Thanks for the question, because I think that helps, allows me to clarify one thing, which is that all of these methods are meant so that they can be applied to single realizations, and they don't necessarily use much information from the training models. Some of them do, some of them don't. And there's differences in what they estimate as the force response, depending on how much information you use from models. And I think this helps to explore the space of how much your estimate of what the force response is informed by how much you have a null hypothesis that the force response is what it is in models, versus the null hypothesis is that we should just trust the observations, long-term trends, and we don't want to use information from models. And these get you slightly different answers. So I agree with you that we should be putting a little bit more weight in the methods that don't rely as much on climate model information. But there are methods that don't use the climate models.
Okay, thank you. We have a question from.
There was Clara had her hand up at some point. I don't know if you wanted to ask a question,
yeah.
Clara. Or...
Oh, thank you. I think Rob actually spoke to it, which was I was interested to hear some discussion of relative roles of aerosols versus greenhouse gases.
Yeah, I think we don't know yet. I think aerosols are potentially a key factor, but we should do some aerosol only simulations with this model and see what it says. But this model has its own biases, and we shouldn't trust it all on its own either. So hopefully we can get more models that can get rid of this ITCZ bias and explore this space a bit more.
Yeah, one issue with this high resolution CSM1, the IHESP, ENSO is very weak, and it has kind of a weak low frequency spectral peak that's kind of between 5 and 10 years. So it is not ENSO as we know it. It has very weak autocorrelation. So I really wonder how that plays into what we're seeing in terms of maybe better simulation of trends, but is this because we have less noise from ENSO in that model because it's underestimated? I think we should be, it's a really important set of simulations, but it's not end all. And I think one has to examine and assess, all the different timescales of tropical variability and really take a bigger view of that model.
Absolutely, we should definitely be careful of getting the right answers for the wrong reasons. And while this model has relatively little ENSO timescale variance, it has quite a lot of decadal variance.
Right.
And I think ultimately what we should be doing with this model is understanding why it does what it does, and seeing if we can get other models to go in this direction too, or if they can provide other explanations for what could be causing this.
Thank you.
So I see we're coming up on the hour. I want to give, first of all, let's just thank our speakers. I think this has been a really wonderful discussion. And thanks to everyone for their questions. If people need to go, they could go, including the speakers. I don't know, we could take a moment to hang around and address a couple more questions, but I also want to be sensitive to people's time.
I'm happy to stay
another-
on, but yeah, thanks everyone for listening, and enjoyed your presentation, Rob.
Maybe we can stay for just 5 or 10 minutes if there are a couple more questions here. Thanks everyone for coming. This is I think the biggest turnout we've ever had for one of these events, and so it's just really great to see that all the interest in the community.
Yeah, thanks everyone.
So let's see, continuing with some of these questions.
Can I take a quick second to address that important thing that Gavin brought up? That
oh, absolutely.
He mentioned that in the Pfeifferdahl figure, the width of the observed trend was only sampling the Hadcrest ensemble, but did not fully account for the structural uncertainty or even the uncertainty in the OLS fit. And this was noted. And I just want to clarify a little bit. I wasn't trying to say the Pfeifferdahl figure was wrong, but that we have a very similar set of situations that we're being presented with here, as particularly the getting at the structural uncertainties associated with the observations is again difficult and something that we should just be fully aware of. So, thank you.
Makes sense. We had a question from.
I was just gonna say, I think there was one other theme that was coming up in the chat, which was about other high resolution models and like high resmip, for example. I don't know if Susanna is still on the call, but she seemed to have some. There seem to be some results from their paper which talk about this. Not sure if still on the call. Might not be. But I mean,
I think she's gone.
She might have gone. Okay, but I mean, just generally, like, I guess question I had is how much of a how much do you think? I mean, probably for Rob, but like do you think that we really should be pushing for a high resolution with coupled models, and particularly like eddying oceans and stuff like this? And I guess you've talked a little bit about there being the CSM1 results, so it's just one model, right? But do you think that do you think it's just it's a fluke with that model, or what, just what are your, I guess it's still to TBD, but what's your gut feeling on those things? Yes.
Yeah, so unfortunately, I don't know about the paper that Susanna was referencing, and I've made note of it to check it out. I do know of some work by Shreya Dame from MPI, who's been looking at the high-res models in the context of these SST trends and finding that the high-res models don't really improve the situation a lot in general. And so my current thinking is that it has more to do with fixing this key bias in the double IGZZ than it does with the high resolution in itself. That said, I think there's a lot of reasons we should be exploring high resolution, and we do know that ocean eddies are a relevant process. There's also mesoscale processes in the atmosphere. You can better represent the topography with just a little bit higher resolution. So if we can run more simulations, including ensembles, at this not the highest resolution people are talking about these days, this intermediate resolution of 1/4 degree atmosphere, 1/10 degree ocean, I think that'd be really valuable. I think pushing to even higher resolution, then you can't do these multiplicadal analyses. And so I would personally advocate for, yeah, more, but not everything to be at this intermediate 1/4 degree atmosphere, 1/10 degree ocean.
Very cool. Thanks for that. And yeah, when you move to the really high resolution, MPI level stuff, you run into it seems like you run into whole new issues with the precipitation distribution.
There was a question from before from Aurelian Reeves about whether I think you showed that the after the La Nina-like pattern, that the high-res CSM2 model is showing a more La Nina-like pattern again, and that you would think that would bring positive feedbacks. Do you also see an acceleration of warming? Do you see something that would be maybe indicative of a change in sensitivity?
I think that's a really promising thing to look into, but I haven't had a chance to myself. I've only had a chance to make that one figure, but I think it hopefully gets people interested to look at the radiation in this model.
That's fair. We have a lot of...
I wanted to note also that if you want to hear more about these mechanisms, that Pedro Denezio has a talk in this seminar series that you can look up.
We have some questions, a lot of questions in the chat. Here's a question for Peter. So the lay plan Huybers map looked like there was a model observation discrepancy in the North Atlantic SST variability of the opposite sense as the tropics. Is there a concern that attention is focused where models might simulate too little variability versus nature, because that ends up being hotspots of apparent discrepancy between trends in models and observations?
Yeah, that's right. The high latitudes actually show the reverse. And we didn't have enough data to really do this properly in extratropical southern hemisphere latitudes, but in the north that does arise. And so I suppose there's a kind of lamppost effect that we have to be a little bit worried about here as well, that we look for where there's big obvious discrepancies, and then we start to center in on them and do statistical tests which are kind of ex post facto, as opposed to thinking about the kind of more global problem and making sure that we don't overfocus on where there are discrepancies that might just be kind of statistical flukes. So yeah, thanks for pointing that out.
And Peter, there was one more question that from Tim Osborne earlier about and when you show the spectra of those simulation data, I know you touched on this a little bit, but were those just control simulations, or did they have some degree of natural forcings?
Yeah, I mean the thing is that they had orbital forcing, they had volcanic events, they had an estimate of solar variability, but you can't really tell the difference between a control simulation because once you get down to these local levels of looking at variability in an individual grid box, it's dominated by the variability that's internally generated within the model.
Excellent. Maybe we'll do... Oh, I'm being told my sound is a bit fuzzy. I'm sorry if that's been an issue.
I can hear you fine.
Maybe we'll do. Okay, maybe we'll do one last question here. I see recent one from Andrew Wittenberg. Question for Rob regarding the statistical methods. Have you evaluated how well they can discriminate the forced internal components in a single realization from a couple GCM where we can determine the actual truth for the model using a forced historical large ensemble?
Yeah, that's exactly the idea of this ForceNet project. So didn't fully explain the details, but these methods are developed and then applied to 10 evaluation members, some of which come from unseen climate models that have a large ensemble, but have not been labeled in any way for the participants. And so then we can test after the fact how well those methods did for these unseen models, and then compute skill metrics. And this is what I mean when one method is more skillful in this evaluation set of large ensembles.
Awesome.
Excellent. Well, maybe we should stop here. Sorry we and everything, but this has been a really wonderful session. And thank you guys so much for bringing these talks and for answering these questions, and again to everyone for coming. And so, yeah, thank you.
Yes, it was great. Thank you for setting it all up. And
Yeah, thanks a lot for organizing. It's a lot of fun.
hopefully we can find things to argue about a little bit more, vociferously at some point, Rob.
Yeah.
I mean, if anything, it's somewhat reassuring that, like, we maybe it's more maybe we're more converged than we thought. I don't know.
We agree what we're confused about.
Yeah, exactly.
To that end, I think we are actually having a talk next session from Alexei Fedorov that's about maybe it's a little bit of each, forced and non-forced. So we'll continue the themes, and maybe there is more agreement than disagreement around this.
I'm struggling to find a way to export the chat so I can respond to people. Can one of you do that and send it to me? I don't know where the button went.
Only with the recording, you'll get it all.
Yeah, we get it
we'll
with the
share that.
recording. Yeah, and then we normally post it along with the video on the ECS Symposium.
Perfect. Thanks.
So yeah.
Just
Thanks.
obviously haven't had a chance to respond to all the questions in the chat and would like to follow up with you.
Yeah, 100%. No, I appreciate that. All right. Thanks, everyone.
Thanks,
Take care.
everybody.